cool. Hi, thank you for making it to the end. I'm sure you're tired. I'm tired, but it's been a fantastic day. Um, I'm here to talk to you about Logos. This is going to be it's kind of a weird talk for me. It's a little bit of a high level introduction. And I would normally talk about political philosophy or like my internal motivations. If you're not familiar with any of my talks, there's some QR codes to some of those. I think for this crowd, like you're already here, so you kind of already internally understand why privacy matters and these sort of things, but you might be interested in corruption, KYC, and the cost of compliance, and how this sort of went hand in hand with the Patriot Act when the 3 towers were demolished. Anyway, so show of hands, who can recognize all of these logos? Okay, all right. Oh yeah, that's expected. For the rest, that's no surprise. Basically, like, you might be familiar with the Onion, Tor. So like on the sides there's Tor and there's the ITP network. The things that look like little bunny rabbits, they are Freenet and Hyphenet. And the one with bullhorns is NuNet, right? And so like these are not like Tor and ITP, you understand probably, like they're anonymizing networks that allow you to basically have censorship-resistant communication while being anonymized and doing so, both in sender and receiver unlinkability. But like Freenet and NuNet were kind of more ambitious than just doing anonymizing networks. They envisioned a civilian internet. They were very concerned about the sort of digital intermediation that is currently happening through all of these sort of big tech platforms are doing, like this sort of neo-feudalism. And they worked on creating this sort of decentralized technology stack that allows you to publish sites outside of like a typical client-server model. And the middle one there, that's Tribler. Tribler is a BitTorrent client, right? It is fully peer-to-peer. They claim they have one of the fastest peer-to-peer search for that, so you can find content within it. And they use onion routing as well to protect you while you're torrenting. That's a university project out of Delft University in the Netherlands. But like this, all of these projects are effectively like 20 years old, right? And like this idea, like there's so much we can still learn from those that I just don't really see actually happening in the space today. And like we should really be continuing that on. In fact, one of the reasons I fell in love with Ethereum is in like the 2014 vision, there was this sort of like heritage of this, where like there was these primitives where you would actually create a vertically decentralized technology stack where you could actually create real decentralized applications. It has been 20 years, and there's quite a few shortcomings, right? Like imagine how it is to access like your, a popular decentralized application today. The reality is if you're on a desktop and you'll probably use your browser, you'll probably type in a URL and click on something. You'll immediately start using a name service to resolve it. Typically, it's DNS. Then you'll be accessing a client-server model, right? Once you've got your front end from that server over the web, it's most likely going to be using some kind of trusted another client-server model in terms of accessing the crypto network, right? In terms of our public mempools, they've become professionalized and become more centralized, and at least in the in like the sort of dominant networks that we have today, our accounts are pseudonymous but public, as well as our transactions. Worse is most of these are actually still happening over ClearNet protocols. And while I've said most of those things, you've probably thought of some project or some startup that has identified this as an issue and has been working to resolve it. But we have protocol fragmentation. If you wanted to be a purist today to access a decentralized application, it's incredibly high friction for an end user to do that. They'll probably have to download like an IPFS node. If it's on Ethereum, you're probably downloading both a consensus client and a execution client, unless you're using Nimbus. And then you have to maintain these. And then finally, if you know where you want to go, you can go, access through a CID or content hash. So kind of like the best in the class that we really have today is like some kind of combination of a couple of protocols, right? If we really care about privacy, you're probably thinking about using an anonymizing network like Tor and combining it with your favorite private transaction systems such as like Monero or Zcash. The issue with this is like, well, you know, a general purpose anonymizing network has its own issues. It's, you know, depending on how you parameterize that network, you know, there's different ways you can trade it off. But if you imagine it as an economy or a socio-political system, something like Tor can't really maintain its economy. It needs to rely on something like Monero or Zcash. At the same time, Monero and Zcash don't really inherently protect the network level privacy. I mean, Monero is doing a great job with Dandelion++ now. But then, like, if you're still, even if you're using this, if you're accessing an application over Tor, it's still inherently relying on like this sort of client-server model, which is quite a shame because like the author has done Freehaven beforehand, and I'm really waiting for him to get back to it. So the question is this the best we can do, or can we do better? The ideal is basically we need to have network-level privacy. We need to have private programmable transactions. Our front ends basically need to be hosted across the entire network and be user verifiable. We need to ensure that you have disintermediated access to these networks and even from consumer-friendly hardware, both in participation of securing the network as well as accessing it from your phone or whatever. Ideally, all of these protocols are integrated in some way, so the friction of actually participating in this network in the way that we envision is done, and of course, it needs to be scalable if we want to have a decent anonymity set. So that's kind of what Logos is trying to aspire towards and what we're building, right? It's not really a new layer, yet another layer one, but it's a private by default decentralized technology stack. While there's many subsystems and many sub-protocols involved, as a developer of a decentralized application, you basically get three major sort of pillars or primitives. So this is anonymous networking and communications, decentralized file storage, as well as private smart contracts. So we can basically, in building such a system, you can split it over these domains of concern. In the interest of time, I'm going to skip it a little bit. And we need a decent foundation to get started with. So we have to start with anonymous communications. We work on a private peer-to-peer messenger / mobile Ethereum client called Status. And over the years, we've learned a lot about anonymous networks. It turns out that depending on the traffic type that you're trying to cover and the sort of trade-offs and properties that you want, there's not like a one-size-fits-all solution. There are issues with onion routing. There are issues with mixed nets. And in our case, there were certainly issues with remailers or flooding gossip subnetworks. So this has led to us creating a sort of framework called libp2p-mix, in which we can actually parameterize for different traffic types. So for example, you'll have, I'll give an example a little bit later on. But here, you're thinking of basically a mixnet in one instantiation, but if you need more throughput, you might consider onion routing in certain scenarios. But here we were largely just thinking about sender unlinkability, right? libp2p-mix is not a transport in of itself, it's an overlay protocol. And so it actually allows us to basically mixify or however you want to anonymize your sort of standard libp2p protocol. And it's all got the good stuff that you'd be aware of, Sphinx packet routing. We can parameterize in different ways, and we have anti-spam measures as well, which is also pluggable. But this is for nodes that have like decent bandwidth. They probably have less churn rates. Maybe they're participating in consensus. So this is kind of like the core of the network, right? But there's also an issue if you're actually trying to connect to this from a high churn device, such as your mobile phone. And so we have like another protocol, which was it's been known as WAKU, where we essentially have a sort of flooding gossip sub network, and it's largely focused on doing receiver unlinkability, right? So you can kind of choose your level of participation in this network, and there's various other sort of sub-protocols towards this, such as like filtering the kinds of messages you actually care about. If you churn off the network, you log off and you want to come back, you might actually want history, right? And if you're developing a decentralized application, there's certain scenarios in which you might want an ordered log, or like the sort of messages you want to send are not really worth putting on more heavier systems. And even though I kind of glossed over that in the interest of time, this is a 30-minute talk compressed into 20 minutes, so I apologize for that. Those two protocols, I also want to highlight just how impactful and transformative they are. And like, if you think about Tor, it has been at the center of some of like the largest sort of revolutions in our modern era, from like the Hong Kong umbrella movement to Arab Springs. And what's interesting about these sort of movements is like they're able to carry capacity. They tend to be like collective emotion. But if there is a chance for change in, say, like regime, very often there isn't any sort of like plan for new governance. And that's where we kind of need to start thinking about a sort of a Lamportian part-time parliamentary sovereignty, or a blockchain, public blockchain. So we provide, we've been developing a sort of integrated multi-chain network. It's, at its core, it's basically, its state transition function is RISC-0. It has zero cache semantics around it. We've developed out a private proof of stake and a parameterized network for block proposal unlinkability. And it's multi-ledger by design because the rate of change in terms of the garbled circuits, MPC, FHE, zero knowledge proofs is changing quite a lot. And we want to be able to have multiple versions of these state transition functions and kind of upgrade or grow with that research. So, the reason why we have RISC-0, the base layer, it uses a UTXO model. The UTXOs is a general purpose data model, and then we can use that in terms of, for doing various sort of state transitions. But we basically use the root chain as for providing services on top of that. And you're probably familiar with block relay censorship as a result of Tornado Cache and so on. And we were thinking about this quite a lot, right? So a lot of people have been discussing like the use of mixed nets for this, but there is a bit of a problem with it. Mixed nets effectively get their anonymity through delays. And so if you're using something like consensus traffic, you have to understand the nature of that traffic. And it's basically a bunch of synchronized senders, right? So let's say you had 100, 1,000, 10,000 validators, or miners or whatever. They're effectively sending a wall of traffic at regular intervals. It's incredibly deterministic. And if you want to put that through a mixed net, it's going to blow out your delays far beyond what you want in terms of a block production rate. In our case, it's 1/30. And so we had to parameterize libpdbmix to basically create a sort of hybrid between these. It's kind of like a hybrid between a flooding gossip sub and a mixed net. And the reason we have to incentivize and disincentivize the cover traffic as well as the allowable block proposals in a certain period. And the reason for doing that is basically constraining bandwidth. So this is basically, you're using things like packets. You do your routing through those. You're sending out 5 different paths, but through a flooding gossip sub. And it turns out that we are able to minimize the amount of bandwidth, get dispersal as fast as possible in approximately 20 seconds. And we believe under an active adversarial model of roughly 20% active adversary and 10% churn nodes, that we can delay the linkability from a block proposer and their block proposal by about 7 years. So proof of stake, making private proofs of stake. I don't want to start any wars here, but like it's probably actually easy to conceptualize this as something like proof of work in terms of how its difficulty adjustments. This is like most proof of stake systems require some like validator set, like a known validator set and a known total amount at stake, right? In our case, we are able to get rid of that, both of those requirements by essentially requiring like the amount that can be at stake to be aged in the previous epoch of consensus. And then when it comes to actually inferring the total stake, we use Roberts-Monroe stochastic approximator. And so what this is basically the ability to be able to learn a value through a corrupt signal. And in our case, that corrupt signal is the block production rate, right? So if we're seeing many block proposals, that means the difficulty is too easy, and so we ramp it up, and the inverse, right? And it turns out in our simulations that we can accurately predict this within like a 3% tolerance. Yeah. I know I'm glossing over, yeah, right? So private programmable transactions. Like I said, this is zero cash semantics. So, you know, if you're familiar with Zcash, it's like shielded transactions. In our case, every coin or UTXO has a ledger ID associated with it for a particular zone that it's operating in. And it has programmable spend rules. The main thing is that kind of different here as we've updated the cryptography a little bit. There's basically two proofs. One's a Merkle mountain range and one's an index Merkle tree for both your commitments and nullifiers. This means you don't need to maintain a giant list of serial numbers. I know I kind of glossed over that. If you're more technical, there's a talk that I did at Protocol Berg. There's a QR code where I talk a bit more about the technical details of that if you're interested. So, yeah, we have this basically like the sort of secure root or core. This is kind of like, you know, we conceptualize this as kind of like a UEFI BIOS, where we actually expect most of the transactions to be happening in like what you might consider to be called rollups. It's not quite like rollups. We call them zones. But they're effectively the same sort of thing, right? You have execution that's happening on these other sort of like chains. And there's a couple of requirements that we need for another service that allows us to do atomic transactions between zones in a private way. They support blobs, they support inscriptions. Yeah, and it's actually very, like, from our data availability sampling, it's incredibly light to verify any zone, which is important for light clients. Yeah, I mentioned one of I mentioned this already, but like we have an intent-like system that's entirely private. We call it PAX, or private atomic cross-zone transactions. Basically, this allows the aggregation of like partial transactions with hidden inputs and outputs. Only the relative balance plus that equals the fees is revealed. Yeah, and these are all these partials effectively ZK aggregated. And gives you this sort of cross-zone consistency proof that allows for transactions between zones. And the fee capture for the executor can also be in a separate partial. So one of the zones we're working towards having at get-go is a way to kind of interface with account-based models and this sort of private UTXO model. So we've been, one way to think about this is it's kind of like Aztec, but you can do things in a single transaction, whether it's public to public, private to private, or vice versa. So yeah, it's a state separation architecture. You can basically run smart contracts both in public or private state, or move between them. Yeah, that's pretty much it. I wish I could go into more detail, but yeah. We care about resource-restricted devices a lot. We're very concerned about being able to run this on laptops and particularly on mobile phones, right, or smartphones. So pretty much anyone that's participating in the network is effectively a light client, is basically helping verify whatever zones that they actually care about. light clients were a by default decision to start with. They have, yeah. So that's it for the sort of blockchain aspects of it, or the multi-chain aspects for it. Who remembers, I mean, you know the Bybit hack, right? Show of hands, Bybit hack? Yeah, okay, cool. Well, for those who didn't, basically you had the continuous integration and deployment of Gnosis Safe was compromised by a hacker by leveraging a Safe employee's credentials. No one was aware of the injection. Gnosis Safe basically worked, except for a target attack on a particular group, in this case Bybit. And this kind of shows the inherent issue of like the client-server models and like why we can't really trust running our front ends on just a website, on a web server. So we've also been working on a decentralized file storage system. It has content hashes that are compatible with IPFS, but it's we disperse the sort of blocks around the entire network to avoid like notions of pinning, or as a result, the inverse of pinning is like censorship, right? We have automatic repair and dispersal. There is a marketplace that we're working on that allows you to collateralize. Yeah, cool, thanks. Yeah, we have Reed-Solomon and Erasure coding. We've been working really hard to try and make this consumer friendly, and we managed to get these sort of proofs down to around 5 minutes with 16 gigabytes of memory, so perfectly adequate on the laptop. And we're working to, we haven't done it yet, so there's still a bit more R&D, but we're working on like oblivious queries. So if you make a query in the network, other participants will not be able to understand, what you're actually querying or the content of it. We also work on open hardware. We're really currently coming out with KeyCard Shell. It's a hardware wallet that has a secure enclave on a smart card. The entire thing is completely open source. We implement a bunch of things. That's pretty much it. I know I've been ranting, I've been going really fast, probably not giving you enough details as much as I would like to give you, but basically what Logos is, it enables you to build private, uncensorable, decentralized applications. So when Zell is happening, it's a little bit early for us to be talking about this, but it's been going on for roughly about 5 years. We're still working on it. We believe that we will have our we have specifications, they're not in a single repo yet. They're between teams and internal documents. We're going to be publishing those. All of these protocols exist already in some form. We need to integrate them, and we believe we'll have a testnet out for this sometime next year. But Logos itself is more than just that. We also want to rebuild civil society. We want to bring crypto into the real world. And so we're building out Logos circles where we're actually starting to exercise like practical politics, do community development, to actually start building out a parallel society or a parallel economy. Yeah. So I also wrote a book on a lot of the sort of motivations and concepts. It's called Farewell to Westphalia. If you go to logos.co/book, there's a PDF you can download. It's CCSA. Logos.co is the website. There's an onion if you're so inclined. But yeah, that's it from me. Thank you.